Welcome to our quantum deep dive.
Hello. Today we're diving deep, really deep, into one of the most ambitious and, well, mind-bending ideas in physics, string theory.
And this exploration is guided by a really fascinating essay by Jürgen Schneppat called String Theory, die Zukunft der Quantenphysik entdecken.
That's our source material.
So our mission today is to unpack this theory for you. We want to explore what it actually is, why physicists even came up with it in the first place.
The truly wild concepts it brings in, extra dimensions, these hidden symmetries.
Right, and the huge problems it's trying to solve, like unifying gravity with quantum mechanics.
And maybe even touch on some surprising ways its ideas are popping up in quantum technology now.
So get ready to challenge how you think about the fundamental building blocks of the universe, maybe even reality itself.
It's definitely complex, but incredibly compelling stuff.
Okay, let's start right at the beginning. The core idea. Our standard physics, the standard model, treats elementary particles, electrons, quarks as tiny dots. Point-like.
Right. Zero-dimensional points, essentially. No size.
But string theory says no.
Exactly. It makes this radical jump. It proposes the fundamental building blocks aren't points at all. They're actually incredibly tiny, one-dimensional, strings.
Like little vibrating filaments, not dots.
Precisely. Either tiny loops or little open segments. And here's the really elegant part. The way these strings vibrate determines what particle we see.
Ah, like different notes on a guitar string.
That's a great analogy. Different vibrational patterns correspond to different particles. So an electron is one specific note, a photon is another, a quark is yet another. It's the vibration mode.
That's quite an idea. Particle properties from Whittles.
It is. And mathematically, this is described by things called world sheets. The string traces through space-time and governed by actions, like the Nambu-Goto or Polyakov action. These depend on the string's tension, basically how stiff it is.
And you mentioned open strings and close the loop.
Yes, exactly. Open strings have endpoints. Closed strings form a loop. And those closed strings are particularly important.
Why is that?
Because when you analyze their vibrations, one mode naturally pops out that describes a particle with zero mass and spin 2.
Which sounds exactly like the graviton, the particle thought to carry gravity.
Spot on. This was a huge early success. It suggested string theory might naturally include gravity, which the standard model really struggles with.
Okay, but here's where things get really counterintuitive. String theory doesn't seem to work in just our normal 4 dimensions, 3 space, one time.
Right. The math is quite demanding. For the theory to be consistent, mathematically sound, you need to avoid things called anomalies. Inconsistencies, it turns out, it requires more dimensions.
More than 4. How many?
Well, for the versions called superstring theory, it needs 10 dimensions in total. And for a later framework called MTheory, it actually requires 11.
10 or 11 dimensions.
Okay.
But we only experience 4. So where are the others hiding?
The idea is they're compactified. Imagine they're curled up, rolled into incredibly tiny shapes, far too small for us to perceive directly.
Like looking at a thin wire from far away, it looks like a line, but up close you see its thickness.
That's the basic idea, yeah, but vastly more complex. These extra dimensions are thought to be curled up into intricate shapes known mathematically as Calabi-Yau manifolds. Specifically, 6-dimensional ones if you start from the 10-dimensional picture.
Calabi-Yau.
Yeah.
And the exact shape of these tiny curled up dimensions is important.
Absolutely critical. The geometry of these spaces, they have a special property, being Ricci flat, which means Rho equals 0 in the equations, is believed to determine much of the physics we see in our large, familiar 4 dimensions.
Like what?
Things like the masses of elementary particles, the strengths of the forces, even which types of particles exist. Our whole universe in this picture is our familiar 4D space-time, sort of multiplied by this tiny, complex 6-dimensional shape.
Now, our universe has matter, not just forces, so string theory needed another ingredient, right? Supersymmetry. Says US why?
Exactly. The early string theories mostly describe bosons force carriers. To get fermions, the matter particles like electrons and quarks, into the picture consistently, you need supersymmetry.
And what does SUI do? What's the idea?
Well, it proposes a fundamental symmetry between those two types of particles. It postulates that every known particle has a superpartner particle with a different spin. So every boson has a fermion partner, and every fermion has a boson partner.
Wow, so it connects matter and forces at a really deep level.
It does. It's mathematically very elegant, described by something called superalgebras. And beyond just fitting fermions in, it also helps with some theoretical problems in physics, like the hierarchy problem, why gravity is so much weaker than other forces, or why the Higgs mass is what it is. Plus, it offers potential candidates for dark matter.
And bringing such UI into string theory led to superstring theory, which, initially came in 5 different flavors.
That's right, yeah. The source mentions them. Type I, type IIA, type IIB, and then 2 kinds of heterotic strings, SO32 and E8 by E8. They differed in details like, whether they had open strings, closed strings, different symmetry groups baked in.
Okay, 5 different versions. Sounds a bit messy. But then things got tidier.
Much tidier, actually. It turned out these 5 seemingly different theories weren't separate at all. They were connected.
Connected how?
Through mathematical relationships called dualities.
Dualities, like 2 different descriptions of the same thing.
Exactly that. A duality means you have 2 theories that look completely different on the surface. Maybe one lives in a tiny space, the other in a large one, or one has strong interactions, the other weak. But they actually describe the exact same physics. They're equivalent.
That sounds powerful.
Yeah.
Linking seemingly unrelated ideas.
It's incredibly powerful.
Yeah.
There's T-duality, for instance, where a string theory on a space curled up really small, radius r, can be equivalent to another theory on a space curled up really large, radius alpha prime over r. Size becomes relative, in a sense. And S-duality relates a theory where forces are very strong to one where they're very weak. So you can study hard problems in one theory by looking at easy problems in its dual.
And seeing all these connections hinted at something bigger.
Precisely. It led Edward Witten in the mid-90s to propose M-theory. This is thought to be an even more fundamental 11-dimensional theory that unites all 5 superstring theories. They're seen as just different corners, different limits of this bigger M-theory picture.
11 dimensions now. And M-theory didn't just have strings.
No, it broadened the picture. It includes not just one-dimensional strings, which are like one brains, but also higher-dimensional objects called brains, short for membranes. You have P-branes, extending in plen spatial dimensions. They have their own dynamics, too.
Okay, brains. So could our universe be one of these?
That's a really exciting possibility explored in brain world scenarios. The idea is that our entire observable universe, the 3 spatial dimensions plus time that we know, might actually be a giant 3-brain existing within this larger 11-dimensional spacetime, the bulk.
And that could explain, why gravity is so weak compared to other forces.
That's one of the key motivations. If the particles carrying electromagnetism and the nuclear forces are sort of stuck living on our 3-brain, but gravity carried by closed strings, the gravitons is free to leak out into those extra dimensions.
Then its strength would seem diluted to us here on the brain.
Exactly. It would appear much weaker than the other forces that are confined with us. It's a potential explanation for the hierarchy problem.
Right, so string theory paints this incredible picture, potentially unifying everything. But it's not without its problems, is it? What are the big hurdles?
Oh, definitely. The biggest one, the elephant in the room, is the lack of direct experimental evidence.
Why is it so hard to test? I mean, we have the LHC.
The problem is scale. String theory predicts that strings and those tiny extra dimensions exist at the Planck scale. That's an incredibly small length, about 10 to the minus 35 meters, which corresponds to unbelievably high energies.
Energies much higher than the LHC can reach.
Vastly higher. The LHC gets to around, 14 tera-electron volts? The Planck energy is more like 10 to the 19 giga-electron volts. That's a huge gap. We just can't build an accelerator powerful enough to probe that scale directly.
So we can't just see a string or the extra dimensions.
Not directly, no. And this connects to another major challenge, often called the landscape problem.
The landscape, what's that about?
It stems from those curled up extra dimensions, the Calabi-Yau shapes. It turns out there seems to be an enormous number of ways to curl them up that are mathematically consistent solutions within string theory.
How enormous.
The estimates are staggering. Something like 10 to the power of 500 different possible shapes, or vacua, maybe even more.
10 with 500 zeros, that's just mind-boggling.
It really is. And the issue is each of these different ways of curling up the dimensions would lead to a universe with slightly different fundamental constants and laws of physics. Different particle masses, different force strengths.
So the theory doesn't predict our specific universe uniquely. It predicts this huge landscape of possibilities.
That seems to be the case, yes. Which makes it incredibly hard to make a definitive, testable prediction. If your theory allows for almost anything, how do you falsify it? Why do we live in this particular vacuum with these laws out of that unimaginably vast number of options?
Are there any proposed answers to that?
Well, there's a philosophical idea of the anthropic principle. Maybe we live in this universe simply because its laws allow observers like us to exist. but physicists prefer physical explanations, perhaps involving cosmic inflation or multiverse scenarios where different regions of space settled into different vacuous, but it's a major theoretical headache.
And string theory isn't the only game in town for quantum gravity, right?
No, absolutely not. There are other important approaches, like loop quantum gravity, which tries to quantize space-time itself in a different way, and things like causal dynamical triangulation. It's still a very active area of research with multiple competing ideas.
So given how hard direct tests are, is there any hope for indirect evidence for string theory?
Yes, scientists are definitely looking for indirect clues. One big search is for supersymmetry. If those superpartner particles exist, maybe the LHC or future colliders could find them.
Okay.
Another avenue is gravitational waves. Future detectors, like the planned space-based LISA observatory, might be sensitive enough to detect subtle signatures predicted by some string theory models, perhaps from cosmic strings or specific inflationary scenarios.
What else?
Ultra-high precision experiments, using things like atomic clocks or quantum interferometers, could potentially detect tiny deviations from standard physics that might hint at quantum gravity effects. And people also look for imprints in the cosmic microwave background rate, background radiation leftover light from the Big Bang, or in patterns of primordial gravitational waves from the universe's very first moments. It's about looking for subtle consequences.
Okay, so testing the core ideas is tough, but here's something really fascinating. Even if we can't test string theory directly yet, its mathematics is proving incredibly useful elsewhere, like in quantum technology.
It's actually one of the most surprising and, frankly, productive twists in the story. The mathematical tools and concepts developed for string theory are finding really powerful applications in completely different areas.
Like what, for example?
Well, techniques related to things like tensor networks, which help describe complex quantum entanglement, and ideas from the complex geometry used for those Calabi-Yau manifolds. These are being applied in quantum computing. They help us understand and simulate the behavior of many interacting quantum particles.
And wasn't there something called the ADC-FT correspondence? That sounds important.
Hugely important, yes. It's a specific kind of duality discovered within string theory. It connects a theory of gravity specifically, one in a negatively curved spacetime called anti-de Sitter space, or ADS to a quantum field theory without gravity living on the boundary of that space.
So it's like a dictionary between gravity in one space and quantum physics without gravity in fewer dimensions.
That's a great way to put it, a holographic dictionary. It lets us translate hard problems in gravity into potentially easier problems in quantum field theory and vice versa. It's become a major tool for studying quantum entanglement, quantum information, and even the nature of black holes.
Wow. And it led to some specific formula connecting geometry and entanglement.
Yes, the Ryu-Takanagi formula. It gives a stunningly simple geometric way to calculate entanglement entropy, a measure of how entangled parts of a quantum system are, by relating it to the area of a minimal surface in the corresponding gravitational theory. Area equals entanglement, essentially.
So these incredibly abstract ideas are actually influencing practical research.
Absolutely. They're contributing to the search for new quantum materials with exotic properties. They're informing ideas about how to build fault-tolerant quantum computers, especially using topological concepts that have roots in string theory. And they're even shaping models of black holes, suggesting they might behave like incredibly complex quantum computers themselves. Models like the SYK model draw heavily on these ideas. Even aspects of quantum cryptography touch on principles explored within string theory.
Wow, okay, so we've gone from tiny vibrating strings and extra dimensions through this vast landscape of possible universes and ended up seeing how these ideas are kind of unexpectedly fueling progress in quantum computing and our understanding of entanglement and black holes.
It's really a testament to the richness of the mathematical structures involved. Even if the ultimate fate of string theory as a theory of everything is uncertain, its intellectual legacy is already proving profound in many ways.
And this deep dive has been guided by the insights from that essay by Jirgo Schneppat we mentioned earlier.
Yeah. You know, they lead you with this really big thought. String theory suggests this almost unimaginable number of possible realities, maybe 10 to the 500 or more, each governed by slightly different rules, if that's even close to true. Well, what does that say about our place in the cosmos? Are the fundamental laws we observe truly fundamental, or just one particular outcome in a vast cosmic landscape?
Very provocative question to end on. Thank you so much for joining us on this fascinating deep dive.
Thank you. Goodbye for now.